Hello everyone, I am Mr. P. Mabu Hussain, Assistant Professor of EEE in Institute of Aeronautical Engineering, Hyderabad. Today, in this video, I am going to explain about the capacitance of a single-phase two-wire line. The learning outcomes of this lecture are by the end of the lecture, the students will be able to understand the effects of capacitance in a transmission line system and also develop the expressions for potential difference between two conductors in a group of conductors. Then develop the expressions for per phase capacitance of a single phase two-wire line. Now let us see what is the capacitance in a transmission line system, how the capacitance exists in a transmission line system. Right, as we know, so any two conductors which are separated by an insulating medium, it constitutes a capacitor, or you can also call the capacitor as a condenser. Right, so this condenser or capacitor can be formed so when two conductors are separated by an insulating medium, or this insulating medium you can also call it as a dielectric. Right, in the same way, in overhead transmission line, two conductors form the two parallel plates, and the air between the two conductors will behave like a dielectric medium. Right, if you take a transmission line system, you have two conductors. Right, so these two conductors will behave like two parallel plates, and between the two lines you will be having the air as the dielectric medium. So this forms the capacitance. Right, so thus an overhead line will be assumed to be having the capacitance between the two conductors throughout the length of the transmission, and this capacitance will also uniformly distributed in the transmission line system over the length of the line, and maybe regarded as a Senti element here. Okay, so the capacitance is a Senti element in a transmission line system. Right, and this capacitance is uniformly distributed throughout the length of the transmission line, and those may be represented with a series of parallel connected capacitors like this in the figure here. And the value of capacitance you can calculate by using the expression C is equal to Q by V. So here Q is the charge on the line in coulombs, and V is the potential difference between the two conductors. Right, then what is the charging current in the transmission line system? Right, now you know that there exists a capacitance between the two transmission line system. Right, and the capacitance will be represented like a series connected condenser here. Now the total series connected conductor, the value will be represented as a single capacitance by connecting them as a lumped element, so that this circuit will form. So see, here is the total capacitance of a transmission line system. Now if you apply some voltage Vs across this transmission line system, so then some current will flow through this capacitance. Now this current is leading the supply voltage. That means if you draw the vector diagram by taking the supply voltage as the reference, then the capacitive current will lead the voltage by exactly 90 degrees. So IC will lead the supply voltage by 90 degrees. That's why you can call this current which is flowing in the capacitor as a leading current. Okay, so and this leading current which will be in quadrature to the applied voltage here, and this current you can also call it as a charging current. Okay, when some voltage is applied across a transmission line, two conductors, so then some current will flow through the capacitance. That current you can call it as a charging current, and the strength of the charging current depends upon the applied voltage here. Right, the capacitance of the line and frequency of AC supply. Right, so this capacitance charging capacitance current or charging current or leading current you can say. So this charging current strength depends upon the voltage applied across the two conductors, and the capacitance between the transmission line system, and the frequency of the AC supply. So these are the three parameters on which the charging current will depend. Right, and this charging current will affect the transmission line by considering some amount of voltage drop. Right, some amount of voltage drop will be there across the transmission line system due to this charging current. So as there is a voltage drop, the efficiency of the transmission line system also will change, right? And also the power factor of the system also will be affected due to this charging current. And the magnitude of charging current you can find by using the expression IC is equal to Vs by Xc, and Vs here is the applied voltage across the transmission line system, and Xc is the capacitive reactance, right? Capacitive reactance, Xc, you can represent it as a 1 by omega c. So if you substitute this value here in place of Xc, so then Ic is equal to Vs by 1 by omega c you will get, right? Now the charging current Ic will be equal to omega c into Vs here, and that omega you can represent it as a 2 pi f. So the charging current Ic is equal to 2 pi f into c into Vs. Now from this expression also you can say that the charging current of a transmission line system depends upon the frequency of the power supply and supplied voltage and capacitance between the two transmission lines. Okay, and the capacitance of the line also proportional to the length of the line. As the length of the line is going on increasing, the capacitance also will increases, and the capacitance effect will be taken up to capacitance effect will be taken only for the transmission line which are having a length more than 100 kilometers or 80 kilometers, right? So if the length of the transmission line is below 80 kilometers or less than 100 kilometers, then the capacitive effect cannot be considered. So the capacitance effect will be generally neglected for short length transmission lines, and this capacitance effect only will be considered for the long length transmission line, and the length of the transmission line will be in the range of 80 to 100 kilometers. Okay, so in the range 80 to 100 kilometers you will not take the capacitance effect. So more than this 100 kilometers you will take the effect of capacitance. So then what are the effects of capacitance on the transmission line system? As I said before, the capacitance of the line is proportional to the length of the transmission line, right? As the length is increasing, capacitance of the transmission line will also be increases, and this capacitance will also be considered only for long length transmission line. For short length transmission line which are up to 100 kilometers, for those transmission line you will not consider the capacitive effect, and the capacitance effect will be neglected up to 100 kilometers. But beyond 100 kilometers we have to consider the effect of capacitance. Then what are the different effects that are there on the transmission line system if the transmission line system is having a length more than 100 kilometers? Okay, let us see, right? If the capacitance of an overhead line is high, right, that means if the length of the transmission line is going on increasing, capacitance of the overhead line also will increase. Now when the capacitance of the overhead line is increased, or if it is high, so then it draws the more amount of charging current. Okay, so see here in a transmission line system you are having the capacitance here, and the current flowing through this capacitance you call it as a charging current, and here you are applying some voltage here. So then if the capacitance value is high, so then this charging current also more. Okay, and this charging current will compensate or cancels the lagging component of load current here. Suppose if here the load is connected, load current will flow, and this load current will be lagging the supplied voltage or receiving end voltage, right? So now when you take the capacitance effect in the transmission line system, and this capacitor will take the charging current, and this charging current will compensate or cancel the lagging component of load current, and hence the resultant current flowing in the load will be reduced, right? So when there exists a reduction in the resultant current, so when the current is decreased in the transmission line system, so then there will be some reduction in the losses will be there, right? So there will be some losses in the line, reduction in the losses will be there, and when losses are reduced, then there will be increase of efficiency will be there. Okay, so then also a reduction in the voltage drop also will be there if the resultant current is decreased. When voltage drop is reduced, then there will be improvement in the voltage regulation. Okay, so here what I want to tell that in a transmission line system, if you consider the effect of capacitance, so then that capacitance will take a charging current, and that charging current will compensate the lagging component of load current. So when it compensates the lagging component of load current, then the current flowing in the transmission line system will be reduced. When the current in the transmission line system is reduced, the line losses will be reduced so that efficiency will be increased, and also voltage drop will be reduced so that voltage regulation will be improved, right? And the other advantage of transmission line is that by having the high capacitance, the load capacity and power factor also will be improved. Okay, so these are the effects of capacitance on transmission line system. So now let us determine the capacitance of a single straight conductor, right? So for calculating the capacitance of a single straight conductor, first we need to determine the electric field and potential difference. So why? Because the capacitance C depends upon the charging charge Q and voltage or potential difference. For getting the voltage, you must know the electric field. Okay, so for that, first you need to determine the voltage or potential difference. So for getting voltage and potential difference, first you need to develop the electric field expressions, right? For that, let us first consider a round conductor, so which is shown here in the figure. This is the round conductor, and this conductor is having a radius of small r and also carries a charge of q coulombs, right? So let us take a round conductor whose radius is small r and it carries a charge of q coulombs. So then the capacitance, so which is the ratio of charge of the conductor to the impressed voltage, will be represented by C is equal to Q by V here. Okay, so now the charge on the conductor gives rise to an electric field. So with radial flux lines like this here in this figure. Okay, the charge on the conductor gives rise to an electric field, so which is in the form of some radial lines, right? If it is a positive charge, then lines will be emanating outside. If it is a negative charge, the lines will be towards the conductor, right? So these flux lines are called the electric flux lines, right? So now the total electric flux is equal to the charge on the conductor. Now according to the Gauss law, electric flux density at a cylinder of radius x meters, when the conductor has a length of 1 meter, can be written as D is equal to Q by A. So electric flux density D can be is equal to Q by A, right? Now Q is the charge and A is the area, right? Here we are considering 1 meter length of the conductor, right? So now when you consider 1 meter length of the conductor and this charge on the conductor is Q here, so then what is the area of this cylinder up to the radius x, right? Up to the radius x, up to these dotted lines, we are considering the area, right? So now up to this distance, the radius is x here, so area will be 2 pi r here will be equal to x. So D is equal to Q by A and A will be equal to 2 pi x. So this is the electric flux density, right? For electric flux density of a cylinder of radius x meters and having a length of 1 meters, right? So once you know the electric flux density, so then you can determine the electric field intensity. Okay, so electric field intensity is defined as the ratio of electric flux density to permittivity of the medium, right? So electric field intensity E is equal to electric flux density D by permittivity, which is represented with epsilon here, right? And the value of epsilon here will be equal to epsilon naught into epsilon r, and epsilon naught is the permittivity of free space or permittivity of air also you can say, and epsilon r value is the relative permittivity, right? So now if you take a transmission line system, so then this transmission line system capacitance is exists between these two conductors, so which is the medium here is the air, so the relative permittivity for air will be equal to 1. So the electric field intensity E is equal to D by that epsilon will become equal to epsilon naught, and the value of D is calculated in the previous slide, which will be equal to Q by 2 pi x. So now if you substitute here in this expression, so then E is equal to Q by 2 pi x into epsilon naught. So this is the value of electric field intensity, right? So the electric field intensity E is equal to Q by 2 pi x into epsilon naught. And this electric field intensity will be represented with units volts per meter, right? So now consider the long straight line conductor which is shown in the figure here. So that is carrying a positive charge, right? So positive charge, and the charge will be Q coulombs per meter, right? So for 1 meter length we are considering here, for 1 meter length the charge on the conductor will be Q coulombs. Also here we are considering 2 points P1 and P2 here on the diagram, so which are located at a distance d1 meters from the center of the conductors and d2 meters from the center of the conductor, and the conductor is at is an equipotential surface in which we can assume that the uniformly distributed charge is concentrated on the center of the conductor, right? The conductor is an equipotential surface, so in which we can assume that uniformly distributed charge is concentrated at the center of the conductor. So now the potential difference which is represented with V12, so which is between the points P1 and P2, so is the work done in moving one unit charge from P2 to P1, right? So this V is the potential difference, or you can also call it as voltage, right? The potential difference between the 2 points P1 and P2 will be represented with V12, and this V12 will be equal to work done on unit charge Q. Okay, so our work done to move a unit charge from P2 to P1. So this is called the potential difference, right? So the voltage drop between the 2 points can be computed by using the integration. Okay, by integrating the electric field intensity over the radial path from P2 to P1. So that means V12 will be equal to integration of your electric field intensity E V over the length from P1 to P2, right? So that length is represented with x, so here will be dx, and you have to integrate the this electric field intensity E from D1 to D2. So the limits will be D1 to D2 you will get. Okay, so this is how you can determine the potential difference between the points of P1 and P2. So the potential difference between the points P1 and P2, which is represented with V12, will be equal to integral of D1 to D2 E dx you will get, right? And here the value of E is Q by 2 pi epsilon naught. So that we are going to substitute here, and you integrate this term completely, right? So here in here there is an x term is there here in the denominator. So here it was not represented. So if you see here in the previous slide, so E is Q by 2 pi x into epsilon naught. So here also you have to substitute Q by 2 pi epsilon naught into x into dx. So from this Q by 2 pi epsilon, this is a constant, you can take it outside. Then you will get integration of d1 to d2 1 by x into dx. Okay, so now this will be equal to Q by 2 pi epsilon naught, and integration of 1 by x you can take it as log x or log x to the base e. Okay, so and the limit are d1 to d2. So this can be written as Q by 2 pi epsilon naught ln d2 minus ln d1 you will get, right? Ln d2 minus d1 you can write it as ln d2 by d1. So the potential difference between the points P1 and P2 which is V12 is equal to Q by 2 pi epsilon naught ln d2 by d1, and this potential difference is represented with volts here. So this is the expression for calculating the potential difference for a single conductor. Okay, single straight conductor here. Okay, so once you know the potential difference, then you can determine the capacitance, right? The capacitance between the points P1 and P2 you can calculate it as a C12, so which is equal to, this capacitance is charge by voltage V12. Okay, so now if you want the capacitance from the conductor surface or the layer of the conductor to at particular point P2 here. So then that here the D1 will become equal to R and D2 will be your distance D. Okay, so in such a case, so the voltage or potential difference V12 can be written as Q by 2 pi epsilon naught ln D by R volts here, right? So now once you know the voltage, so then capacitance C is equal to Q by V here. Okay, so like that you can determine the capacitance, right? For calculating the capacitance, first we need to calculate the voltage or potential difference between the 2 points. So then you can calculate the capacitance by using the expression C is equal to Q by V, right? So now here we calculated the potential difference of a single conductor by considering 2 points P1 and P2, which are at a distance D1 and D2 meters from the center of the conductor. Now you follow the same procedure and let us determine the potential difference between the two conductors in a group of conductors. Okay, so here instead of taking one single conductor, we are going to take a group of conductors and we are going to find out the potential difference between any two conductors in the group. Okay, so let us assume that here you have a n group of conductors are there. So those are represented with 1, 2, here I, K, M and N, right? So the conductors are represented with 1, 2, 3 like that up to in the middle we are taking two conductors as I, K, M and then and so on up to N. So total of n conductors are there in the system, and the distance between any two conductors you can represent with a capital D. Okay, so that's it, the distance between the two conductors 1 and 2 you can call it as D12. So the distance between 1 and K, so you can call it as D1K or DK1 like that. Okay, right. So after taking the a group of n number of conductors and after labeling these conductors and representing the distance, here we have for calculating the potential difference between any two conductors, we are making some assumptions here, right? So the assumptions here are the conductors are far away from the ground. We are assuming that all the conductors are far away from the ground, which means that the effect of earth will be neglected here. Okay, the effect of ground or the effect of earth is neglected here. Why? Because the conductors are placing far away from the ground. So then the second assumption is that the conductor radii is much smaller than the distance between the conductors, right? If you observe the distance between any two conductors, so then the distance between the two conductors must be very high or must be high when compared to the radius of the conductor. Okay, and the last assumption is here is that the charge on the conductor is uniformly distributed along its length, right? So the charge on the conductor is uniformly distributed along the length of all the conductors. So then in such a case, the sum of all the charge in each conductor will be equal to 0. So that means Q1 plus Q2 plus up to Qn. So that value will be equal to 0. Okay. So these are the assumptions what we are making for determining the potential difference between any two conductors in a group of conductors, right? So now here assume that a conductor M has the charge Qm coulombs. Okay, so each conductor from 1 to N will be having the charge. So those charges are represented as Q1, Q2, Qi, Qk, Qm and Qn like that. Okay, so here we are considering the conductor M here, and the charge on the conductor M will be Qm coulombs per meter. Okay, so now the potential difference between the conductors K and I due to the charge on the conductor M we are going to calculate here. Okay, so we are going to calculate the potential difference between two conductors I and K due to charge Qm. Okay, so this is represented as Vki in bracket Qm. So this, which means that potential difference between conductors K and I due to charge Qm, right? So this expression you can write from the previous expression, which is this one. Okay, so that by using that expression, this value will be equal to charge qm, what we are going to consider that value, by 2 pi epsilon naught ln, and the distance from ith conductor to mth conductor, which is dim, and the distance from kth conductor to mth conductor, which is dkm. Okay, so this is the potential difference between the conductors I and k due to charge qm, right? So like here you are having many number of charges here, q1, q2, q up to qn are there. Now we calculated the potential difference between k and I by considering only the charge qm, right? If you take all the charges from q1 to qn, so then you can have the number of equations like this, right? Suppose if you want the potential difference Vka, so which is the potential difference between the conductors k and I, Vka is equal to, due to charge on the conductor 1, which is represented as q1, will be equal to q1 by 2 pi epsilon naught ln d I2 1 di1 by di, so the dk1, right? So similarly, if you want the potential difference between the conductors k and I, so due to charge q2, so this can be written as q2 by 2 pi epsilon naught ln d I2 by dk2. So like this you can write up to the charge qn. So by considering the charge qn, so potential difference V between the conductors k and I due to the charge qn will be equal to qn by 2 pi epsilon naught ln d in by dkn. So like this you can have the number of equation. Now the total potential difference due to all the charges between the conductors k and I will be written as Vki, right? So this will be equal to sum of all the values, right? So here Vki, so which is the potential difference between the conductors k and I, this will be equal to Vki due to charge q1 plus Vki due to charge q2 plus and so on up to Vki due to charge qn you have to consider, right? Sum of all the potential differences due to all the charges you have to consider. Okay, so now when you do the sum here, so this term 1 by 2 pi epsilon naught, 1 by 2 pi epsilon naught, this 1 by 2 pi epsilon naught is the common, right? So you can take it outside here. So 1 by 2 pi epsilon naught, and this summation you have to take from m is equal to 1 to n, right? So m here represents the number of conductors from 1 to n here. So then qm ln dim by dkm. So this is the expression for calculating potential difference between any two conductors due to charge on all other conductors, right? This expression is a very important expression. So by using this expression only, we can calculate the capacitance in any number of conductors transmission line. So if there are two conductors, so which is called a single phase transmission line system, so then here the value of m will become equal to 2. So if it is a three phase transmission line, the value of m will become equal to 3, like that. Okay, you can take any number of conductors transmission line and you can calculate the potential difference. Once you know the potential difference, then the capacitance will be found out easily by using the formula Q by V here. Okay, right. Let us see the capacitance of single phase two-wire line. So then you can understand that. Okay, so in a single phase or two-wire transmission line system, you will be having two conductors, right? This is first conductor and this is second conductor. And let us assume that the distance between these two conductors is capital D here. Okay, and the charge on each conductor is represented as Q1 and Q2. And charge distribution is such that the sum of Q1 and Q2 will be equal to 0. So that means the charge on the conductors is uniformly distributed such that Q1 plus Q2 will be equal to 0. And you also assume that the radius of conductor is one is R1, radius of conductor 2 is R2 here, right? Now here one conductor act as a forward path, another conductor is act as a reverse conductor, right? So the charge Q1 will be equal to minus Q2, you can say. Okay, so Q1 and Q2, which will be equal to, so suppose if Q1 is having a charge Q, then Q2 will be having a charge minus Q. So why? Because one conductor is forward conductor, another conductor is a reverse conductor. Okay, so for calculating the capacitance here, first you need to determine the potential difference between the two conductors, so that you can calculate the capacitance by using the expression C is equal to Q by V. So first you have to determine the potential difference between the two conductors 1 and 2. For calculating the potential difference between the two conductors 1 and 2, here also we are making some assumptions. So the assumptions are, first one is conductors are far away from the ground. Right? Conductors are far away from the ground in the sense the effect of ground or the effect of earth we are going to neglect here, right? And the conductor radii must be smaller than the distance between the conductors. These are the assumptions we are making. And also the charge on the conductor is uniformly distributed such that Q1 plus Q2 will be equal to 0. So these are the assumptions what we make while before we are calculating the potential difference between the two conductors, right? So now you recall the equation, potential difference between any two conductors in a group of conductors. Okay, so the same expression you can take here, and by considering M is equal to 2. Okay, so now the potential difference V12 can be obtained in terms of Q1 and Q2. So by using this expression here, okay, the value of N, number of conductors here, will be equal to 2. So the summation you have to calculate by considering M is equal to 1 to 2 only. Okay, so V12 is equal to 1 by 2 pi epsilon naught summation M is equal to 1 to 2 Qm ln D 2M by D 1M here. So here in the previous slide we calculated the VKI, right? So now here the distance in the numerator will be D Ik and denominator is dk dim, sorry, and denominator dkm, right? So here we are calculating the potential difference between 1 and 2. So in the sense k will be equal to 1 and I will be equal to 2 here. So this will become d 2m by d1m. Okay, so here if you observe the ln terms will be d2m by d1m, right? So this expression we have to use for calculating the potential difference. Now substitute m is equal to 1 and m is equal to 2 here in this expression and expand the equation, right? Then V12 will be equal to 1 by 2 pi epsilon naught. When if you take m is equal to 1, then this expression can be written as Q1 into ln d21 by d11 plus, so if you take m is equal to 2, Q2 ln d22 by d12 you will get. Okay, so now here as I said before, this is a single phase transmission line in which one conductor is acting as forward conductor, another conductor is acting as a reverse conductor. So if Q1 is equal to Q, so then Q2 will be minus Q. Okay, so here Q2 is equal to minus Q1 also you can say. Okay, so Q1 is equal to minus Q2 or Q2 is equal to minus Q1 you can say. So why? Because one conductor is acting as a forward conductor, other conductor is acting as a reverse conductor. And the value of D21 and D12, so this is the distance between the conductors 1 and 2. So the distance between the conductors 1 and 2 is capital D here. Okay, so this is the distance between the two conductors. And the value of D11 and D22 here will be equal to the radius of each conductor. Right, D11 is nothing but the radius of conductor 1, which is R1. D22 is the conductor radius, second conductor radius, which is R2 here. Okay, so then this expression can be written as V12 is equal to 1 by 2 pi epsilon naught Q1. So ln in place of D21 you can write capital D, so which is the distance between the two conductors. In place of D11 you can write R1, right? So then minus Q2 will be equal to minus Q1, so here minus Q1 we are taking ln, and D22 is R2 and D12 is capital D. Okay, so you are getting, so V12 is equal to 1 by 2 pi epsilon naught Q1 ln D by R1 minus Q2 ln R2 by D here. Okay, so this expression even you can write it as Q1, you take common here in the both the terms, Q1 by 2 pi epsilon naught ln D by R1 minus ln R2 by D you will get here, right? So now log A minus log B expression, if it will be log A by B you can consider. So this will be equal to Q1 by 2 pi epsilon naught ln D by R1 by D R2 by D you will get. So this can be written as Q1 by 2 pi epsilon naught ln D by R1 into D by R2 you will get. Okay, so D by R1 into D by R2 you will get. So now this expression even can be written as Q by 2 pi epsilon naught ln D square by R1 R2 you will get, and this even can be written as D by R1 R2 underscore it whole square, and this square will come here, so that you will get final equation will be equal to Q by pi epsilon naught ln D by underscore it R1 R2. Okay, so here 2 will get cancelled, so V12 is equal to Q1 by epsilon naught ln D by underscore it R1 R2. This is the potential difference between the conductors 1 and 2. Okay, so now the potential difference between the conductors 1 and 2, so V12 will be is equal to Q by pi epsilon naught ln D by R. So from the D by R1 R2 which is under square root. Okay, so now the capacitance between the conductors 1 and 2 will be equal to charge Q by Q1 by V12, right? So charge Q1 by V12. Now here Q1 by pi epsilon naught ln D by underscore it R1 R2 will get here, and Q1 will get cancelled. So C12 will be equal to pi epsilon naught by ln D by underscore it R1 R2. So this is the capacitance between the lines 1 and 2, right, which is called the line capacitance. So which is called the line capacitance. The line capacitance value is C12 is equal to pi epsilon naught by ln D by underscore it R1 R2. Now if the radius of the two conductors are same, which will be equal to R, so then this equation can be even written as C12 is equal to pi epsilon naught by ln D by R you will get. And the units here are the farads per meter. Capacitance units is farads, and this capacitance we calculated by considering the conductor to be only 1 meter. So the capacitance units here is the farads per 1 meter. Okay, and you also know that epsilon naught value, epsilon naught will be equal to 8.85 into 10 power minus 19 you will get, I think so, right? So you substitute here epsilon naught value, so that you will get the final expression as this one. So 0.0121 by ln D by R, right? So log here, if you are representing the log, then base will be E, right? So now this is called the line capacitance, right? The capacitance between, so once you check this value, so epsilon naught is equal to 8.85 into 10 power minus 24, I think so. So farad per meter. So once verify this value and substitute that value here in epsilon naught, so that you will get this expression. Okay, and this capacitance C12 is the line capacitance which is between the conductors 1 and 2, right? Now here the value of C12 is represented between the conductors 1 and 2. Now if you want the per phase capacitance or line to neutral capacitance, you have to locate the neutral first, right? So in a single phase transmission line system, the neutral will be in general in the middle of the two conductors, right? So here in the middle of the two conductors you will be having the neutral. Now this capacitance is divided into two parts, C1n and C2n here, and the value of C1n and C2n both will be the same here. Now if you see here this configuration, the total capacitance, so which is C12 is the parallel combination of this C1n, sorry, not parallel, series combination of C1n and C2n. Okay, so when the two capacitors are in series, the total capacitance you can write it as C1n into C2n by C1n plus C2n, and also the value of C1n and C2n, so both are the same. So this can be written as C12 is equal to C1n multiplied by C2n, you can write it as again C1n. Why? Because these two are the same, by 2 C1n, and C1n will get cancelled. So the value of C1n will be equal to 2 times the C12. Okay, so the capacitance between line 1 to neutral will be equal to 2 times the capacitance between 1 and 2 conductors, right? This will be same as for C2n also. So C2n will be equal to 2 into C12. Okay, so the capacitance of the conductor between one conductor and neutral, so which is C1n or C2n, so this value will be equal to 2 times the C12. Okay, so 2 times the C12 here, C12 is the in the previous slide this value is 0.0121 by ln d by r, or you can even write it as 2 into, so pi into epsilon naught, this value, right? So pi into epsilon naught by ln d by r also you can write. Okay, so that means 2 pi epsilon naught by ln d by r will be the value of capacitance between one conductor and neutral, right? So if you substitute the epsilon naught value here and calculate the value, you will get 0.0242. Okay, so the capacitance between one line and neutral will be equal to 0.0242 by ln d by r. Here is this value is in microfarads per kilometer. Okay, see here in the previous slide, so the value of C12 here, so C12 is equal to pi into epsilon naught by ln d by r. So this value is in farads per meter, right? Now this can be converted into farads per kilometer by multiplying with 1000, right? And again by substituting the values of pi and epsilon naught and calculating the value, and this C12 you are getting it to be equal to 0.0121 by ln d by r, and that value is in microfarads per 1 kilometer. Okay, so if you want to the capacitance value per kilometer, you can use this expression. So per meter you can use this expression, or you can use this first expression itself for calculating the capacitance, which is in terms of farads per meter. And if you want for 1 kilometer, simply you have to multiply with the 1000. Okay, so it is always good to remember the first equation so that you can calculate the capacitance for any for meter length or for kilometer length easily, right? So once the capacitance value is calculated, so then the associated charging current, so the charging current I is equal to, the formula is omega c into applied voltage, and this charging current is a capacitive charging current, and it will leads the applied voltage by 90 degrees. So it is a complex term which is represented with J. J here is the 1 at an angle 90 degrees. Okay, so this is the phase current. IC is equal to J into omega into C into V, right? Here C is capacitance between the two conductors, which is C12, and voltage is voltage between the two conductors, P12. Okay, and current will be represented in ampere, and this amperes is for 1 kilometer, right? So if you take per meter length, this will be in meter length only you will get. Okay, so like this you can calculate the capacitance between two conductors in a single phase two-way transmission line system. So for calculating the capacitance, always you have to first calculate the potential difference, then you can calculate the capacitance by using the expression Q by V. Okay, and also we know that we have made some assumptions while calculating the potential difference, right? The assumptions are the charge on the capacitor, charge on the conductor is assumed to be uniformly distributed. So suppose if you take a practical case, in the practical case the charge on the surface of the conductor is not uniformly distributed, right? So if you consider the non-uniformity of charge distribution, so then the capacitance per phase to neutral you can calculate by using this expression. Okay, Cn value is equal to 0.0242 by ln d by 2r plus d square by 4r square minus 1 whole to the power of 1 by 2. So which is in microfarads per kilometer, right? So when you are using this expression 0.0242, so this log term will be to the base 10, right? Suppose if you are using the capacitance Cn is equal to 2 pi epsilon naught by, so the here log term will be to the base e. So here you have to consider this to be ln, and here you have to consider it to be log to the base 10. So you keep remember this value. So d by 2r plus d square by 4r square minus 1 whole to the power of 1 by 2. Okay, and also we assume that cross section of each conductor is assumed to be circular. So but it is not the case for a practical transmission line system. In a practical transmission line system we use the stranded conductors, right? So in which the conductors are not exactly the circular one. So but the effect of that will be neglected in general. Okay, right? So this is how you can determine the capacitance of a single phase two-wire line. Thank you very much.
Like, share and subscribe. Hit the bell icon for more updates.